So the next presenter, I already had the chance to touch a die that is out of plastic, which is funny. It's the only die that you can cut with a scissor. It's Emre Ozer. He leads the ambitions around flexible processor architectures at Pragmatic, which is a non-silicon production process with flexible dies. So, thank you very much, Emre.
Okay, all right. Thank you, Stefan. So, yeah, I work at Pragmatic Semiconductor in Cambridge, UK. So I'm going to present, hopefully, an interesting concept called the first non-silicon RISC-V processor. So let me talk about the company Pragmatic Semiconductor a bit. So we make integrated circuits on flexible wafers, so we call them flex ICs. So when I use the term flexible, I meant literal. So there is no metaphorical here. So they are physically flexible. So the technology uses thin film transistors, or TFTs, that is used in the literature, that is called in the literature. So the semiconductor material is not silicon. So it's called metal oxide IGZO material, Indium-Gallium-Zinc-Oxide. So Pragmatic Semiconductor fabricates these devices, TFTs, resistors, capacitors, on polyamide wafers like this. So this is a standard 200 millimeter wafer, and the substrate is polyamide, extremely thin, 30 micron. The substrate, and the devices are fabricated on it. What we call is using low-cost lithography. So that makes the chips low-cost, very thin, and physically flexible, or sometimes we call it bendable. So the company, as I said, I'm based in Cambridge. We have two sites. The headquarters is in Cambridge, UK. But our fabs are also in the UK, so in a city called Durham, the northern England. So there's a picture of our warehouse there, and the fab currently, the one in the red box, is a very compact fab, about 1,000 square meters. You can see that it's not populated a warehouse, so we are planning to populate the entire thing with different fabs. Every year we'll add another fab there. So we started in 2010. Currently we are about 370 people. Now that's the core of the presentation. So I'm going to talk about the first non-silicon RISC-V microprocessor. So we call it Flex RV. So it has some integrated, very simple ML accelerator inside as well. We implemented the chip, we fabricated, as well as we assembled the chip on a flexible PCB, something like this. I can wave it while, something like this, so you can maybe see me afterwards, so you can and hold it as well yourself. So. And we demonstrated the functionality of the chips while it's flat as well as while it's bent. So I have a video for that. So this was, again, not a sole activity. We always collaborate with partners. So this was in collaboration with Harvard University as well as Qamcom, which is a company in Sweden. And the work was published in Nature last September. And people always ask me, okay, yeah, it looks cool, but what's the use? So the main use for this type of processors is what we call extreme edge. So extreme edge, something we came up with. The way I define this is that it is the domain where conventional electronics cannot be integrated because of several reasons. It's not PPA. It's mainly cost, form factor, conformability. What I mean by that, the electronics is taking the shape and the contour of the surface is attached. And then user comfort. These are all qualitative things, but very important. The current silicon technology cannot address many of these things. So good examples are like fast-moving consumer goods, FMCG. So what I mean by this is like drink bottles, packaged food, the personal care things, everyday things we use, and we use very, very fast. And the electronics are embedded. Electronics can be embedded into their labels or packaging to make them smarter, so you can interact with the products you buy. So they are very cost sensitive. So if the chip costs more than 5 cents, you don't have a business there. That's so sensitive. The other one is healthcare, like the healthcare patches, ECG, EMG type of patches. Smart dressings, what I mean by that is like the wound monitoring, like with Band-Aids. You haven't seen any of these being enabled with electronic because of the cost and form factor and user comfort reasons. It's nothing to do with PPA. The other interesting emerging area is e-textiles, so electronic textiles like smart garments, smart carpets, where the conformability and user comfort is a key factor. And agriculture as well, so there's a lot of interest on monitoring plant growth to increase the yield. So here is the architecture of the Flex RV. So again, we use open source Serve processor, CPU. It's 32-bit, RV32i compliant. We did some changes so that it supports the only RV32E, so we can reduce the number of registers. So we try to make sure that the Flex RV is as small as possible. And we added a very tiny ML accelerator, tightly coupled with 4 custom instructions. And it's an SoC, so it's not just CPU. So there are very simple peripherals in it. And one thing, if you notice that there is no memory, today we can't really integrate large on-chip memories. What I mean by large is just several kilobytes. So our solution was that let's use something in off-chip that we get the code and data off-chip, from off-chip to on-chip. The other thing is that we are not accessing the memory, off-chip memory, using parallel wires. It's actually, we added a SPI interface, custom SPI interface, so we also access the memory in bit serial manner. The reason why we did this is that it simplifies the assembly process, because if you access memory in parallel, then you have to have a lot of pads, chip pads, and this will make the assembly process, which is also a novel thing. That's why we restrict this. So the assembly process should be simpler. So if you look at the implementation results, you can see that it contains around 13,000 NAND2 equivalent gates. So this is quite impressive for this technology, and the implementation clock frequency is 61 kilohertz. So the first thing we did is we fabricated the wafers, and then we did the wafer level tests. We find the functional dies first, and then we dice the wafers, take out the functional dies and attach them to a flexible PCB. So you can see that this is the picture. So the rectangle in the middle is the chip, and the rest is the flexible PCB. So we attach the chip directly from dice wafer, and using non-conductive and conductive adhesives directly to the flexible PCB. And the PCB is connected to a test harness where it's connected to an FPGA. FPGA essentially emulates the off-chip memory, providing the data and the code to the processor. And also the processor output through GPIO was sent to FPGA, and FPGA displays connected to a laptop. The laptop's display is used to show the results of the running program on the processor. So we measure the average and maximum frequency of the tested chips and number of chips. So average is 52 kilohertz, but max we can reach up to 60 kilohertz. So this is also quite interesting. You won't see this in the silicon world. So we did a dynamic bendability test. So what I mean by that, the FlexRV is running a program, and then we start flexing or bending the chip in two different modes. So tensile, the tensile means that the chip is, so what we have done is we got plastic cylinders with different radii of curvature, like 3 meter, 4 millimeter, and 5 millimeter. We wrap the PCB around that flexible, that plastic cylinder while the program is running. And so we bend the chip inward like this. This is called tensile mode. If you roll it in the opposite direction, then the chip bends like that. So, and then we measure their maximum frequency. This was just an interesting test. So we like to know whether the chip can still function. And actually, they function up to 3 millimeter, whether it's tensile or compressive. The interesting thing is that if you bend the chip tensile, the chip gets faster. If you bend it compressive, it gets slightly slower, like at 2% maybe faster, and in compressive it gets 4% or average slower. The reason is that when you stress the chip, mechanical stress the chip, then the transistor mobility and the threshold numbers of the transistors change as well. So I have some live demo here. Hopefully it will work. There's no audio in it, so it's just showing what the PCB is, what the chip is, and the test harness, and the live video will start. So this will show the test we did for the bending around the 3 millimeter plastic cylinder. So it's in the flat mode now. And it's running a hello world. So we are now rolling around the cylinder to bend the chip in tensile mode. Video gets fast forwarded, so that's not the speed of the processor displaying the result. Now we are unrolling it to make it flat. Now we are gonna roll it in the opposite direction to bend the chip in the compressive mode. And you can see, actually there is some anomaly happen on the screen. If you notice it, you can tell me later. It's an interesting one. We left it that deliberately. Now it's flattened again, and it's still the processor is still running with one anomaly there. I don't have time to go into that to discuss with you here, asking all of you whether you've seen it or not. So let me move on. That's it. So I presented the first non-silicon RISC-V processor. It can actually run arbitrarily, compile high-level programs like C. This is what we did as well. I didn't go into the details, but we have a lot of different programs written in C. We compile and run it. And there is also an integrated ML accelerator in it with supported with the 4 custom instructions. And we demonstrated for the first time, I think in the non-silicon world, we actually demonstrated the entire system assembled on a flexible PCB and running the programs and while they are flexed. All right, so this is my contact details. I'm happy to take questions as well.
Thank you very much. I think, again, we have time for one question.
There's one there.
Oh.
There.
Yep.
Yeah.
there's a question over here. This might be a quick one.
Oh, so
Over
we
here.
already have one.
Sorry. Given the serve as a serial core and you have serial memory interfaces going in, are you able to keep the entire pipeline busy with the serial memory in and the serial
It's a single pipeline processor. Serve is a single pipeline.
Oh, serve, not
Yeah.
swerve.
Serve.
Okay.
Yeah. So it's there is no multiple pipelines. So what we have done is we stop the clock when we access the memory, so everything stops there, so it doesn't move. But that's a good point. So the CPU has to wait for the memory, especially if it's a load instruction, it has to wait until the data comes back.
Okay. It's interesting. Might be interesting to look at swerve. It's properly serial.
So sorry, we're running a bit over time. So I think you're here for the evening, right? So it's a good opportunity for socializing, asking more questions.
I'm here tomorrow as well. So
and everybody wants to touch the die. So. Thanks again to Emre.